This is Magic 063 Differentiable Manifolds. I'm Camille Mackenzie, and this podcast is about looking at tangent vectors in the case of zero sets in Rn. These are concrete examples, and they're good illustrations of the general process. So start off with a surface in R3 simply defined as f inverse 0, where f from R3 to R is a smooth map and has rank 1 at every point of the zero set. So that zero set will be the manifold M, and take a point in it, x0, y0, z0. The usual way to get the tangent plane, and I emphasize plane here rather than space, is to first of all find the grad, standard formula there for the grad of f, and that vector is normal to M, and what's more, it's non-zero at every point of M due to the rank condition. The rank condition is that the derivative matrix have rank 1 at all points, and the entries of the derivative matrix, it's a row matrix, and the entries are the three partials. So at every point of M, at least one of those is non-zero, and therefore the grad is non-zero. Of course, I'm emphasizing here that the grad is a vector, whereas the derivative matrix is a matrix. And when we come to talk about these things in the general setting of abstract manifolds, they'll be quite distinct. So we've got the grad, which is non-zero at every point of M, and it's normal to the surface at the point where we take it. So, usual thing, write n0 for the unit normal vector, and the tangent plane, and again, that's talking about the plane, is given by this vector equation. R is the variable, r minus x0 must lie in the plane that means perpendicular to n0. And a tangent plane to any surface in R3 can be considered as a vector subspace of the tangent space to the whole of R3 at that point. And so we get the usual picture in which you take the tangent plane at some particular point of your surface and simply regard the point as the zero of a tangent space structure on that plane, and you simply add by the parallelogram rule in the plane like that. And that's exactly what's meant by saying that it's the vector subspace of the tangent space of R3 at that point. Let's see what that comes to in terms of coordinates. M is given as a zero set, and it's a non-trivial result that charts exist. I won't go through the details of that, but suppose that we've got a chart on M with x0 actually in the domain U there, and I'll write little u and little v for elements of R2, so that phi of x0 will be u0, v0. Then define a curve in M. Gamma t is equal to phi inverse of u0 plus t, comma v0. So holding v0 constant and letting u0 vary, we get a curve in M. And at time t equals 0, that passes through the point x0. Of course, this is exactly what we did, looking at a basis for the tangent space to an abstract manifold induced by a coordinate system around a point. I'm doing it again in this concrete situation of a surface in R3. Now, our gamma's in F inverse of 0, so F comp gamma is constant at 0, and therefore when we differentiate, we get this equation here, which is precisely that the grad of F dotted with d gamma dt is 0. In other words, gamma is in, or rather, d gamma dt is in the tangent plane to the surface. And of course, that's what we expect. In fact, the tangent plane to the surface, which is the kernel of the derivative matrix of F, consists of all linear combinations of d gamma and the curve that you get by allowing u naught to be fixed and v naught to vary. We'll come to that in a moment. And that we get that result by applying the Rake nullity theorem to the derivative matrix to check that all the linear combinations of these two tangent vectors belong in F, and that is the correct, belong in this tangent plane, and that is the correct dimension. Okay, so going back to gamma, gamma dot 0 is a non-zero element of the tangent space 2M at the point x0. And here we've got the corresponding business of holding u naught constant and letting v naught vary. That gives a curve which I'm denoting xi t. These are just temporary notations. And the two tangent vectors to gamma at 0 and to xi at 0 form a basis for the tangent space 2M. So for surfaces in R3, given as zero sets, the tangent space can be identified with the ordinary tangent plane. And I'm confident that you've encountered this before. I'm going over it again because we're now in the setting of abstract manifolds and can appreciate this as a special case of the abstract constructions. And now let's look at the case where the target dimension is more than 1, a general smooth map from Rk to Rp, which has maximal rank P, so K is greater than or equal to P, maximal rank P at every point of the zero set. And there's going to be two examples. This is the first one. In fact, they both are from R3 to R2. Here's the first one. It's given by this formula. F of x, y, z, first coordinate is x squared plus y squared plus z squared minus 4, and the second one is x squared plus y squared minus 1. And you can check that the rank of this F is 2 at every point of the zero set. And I urge you to do that. Now, M is the intersection of the zero set for the first coordinate. The first coordinate, zero set, is simply the sphere of radius 2, centre the origin. And the zero set for the second coordinate is a cylinder along the z-axis, radius 1. So M itself is the intersection of the sphere, this sphere, and the this cylinder. And it's fairly easy to visualize. Imagine here's the sphere, and down the middle, this is perhaps not truly to scale, but you'll get the idea easily enough. There's the cylinder, and let's change colours briefly. The intersection will be the circle up here, And down here, this is hard to do convincingly. Okay. But you can visualize that mentally, I'm sure. The intersection is the union of two circles. First of all, the circle of radius 1 in the plane z equals root 3. That's up here, of course. And the circle of radius 1 in the plane z equals minus root 3. So the intersection is disconnected. It has two connected components. They're both of dimension 1. Everything is fine. This is a perfectly good manifold. And the tangent spaces or tangent lines to these circles are lines that lie in these planes z equals root 3 or z equals negative root 3, just in the ordinary way of tangent lines to the circle. And I urge you to check that these lines are actually the intersections of the tangent plane to the sphere and the tangent plane to the cylinder at the points of M. Okay, so that's a good exercise. That's a well-behaved example. And even if we were going from R37 to R23, if we have maximal rank at every point of the zero set, then corresponding statements would be true. The zero set would be a well-defined manifold of dimension, what did I say, 37 minus 23, so it would have dimension 14. And the tangent spaces to the intersection, to the zero set, would be the intersection of these 23 hypersurfaces of dimension 36. Let's not do an example in detail of this, but exactly the same principle would hold, that the tangent spaces to the intersections would be the intersections of the tangent spaces. Here's another example. This is M prime defined as the zero set for a G from R3 to R2, and the first component is exactly the same. The zero set for the first component is the sphere of radius 2 centre of the origin. The second component has zero set, again a cylinder, again radius 1, but it's been shifted 1 unit along the x-axis. And this makes a great difference. Work out the rank for this. You'll find that it has rank, there's a typo there. This has rank 2. Okay. Okay, let's get that right. This has rank 2, maximal rank, at every point of M prime, zero set, except the point 200 at which it has rank 1. And that is a problem point. And again, I urge you to check that for yourselves. M prime is still the intersection of the sphere, that's the zero set of the first component, with the cylinder, which is the intersection of the zero set of the second component. That part is still fine, but this intersection is actually a closed curve, and it has a point of self-intersection at 200. And again, I urge you to find the curve. It's a simple matter of solving two quadratic equations simultaneously. And what you can also do, these exclamation points are meant to indicate exercises. This curve can be parameterized in the ordinary way as a smooth, regular curve. As such, it has no problem at all, except that it has this point of self-intersection. So as a parameterized curve, there are two different parameter values for going through 2, 0, 0. And they both give rise to a non-zero tangent vector, but they're different tangent vectors. In fact, they're linearly independent. Okay. So you have a problem. You might be tempted to say, well, okay, we've got two linearly independent tangent vectors, so they generate a plane, and we'll take the plane as the tangent space. But not every vector in that space will be tangent to a curve in the intersection. Really, only the scalar multiples of each of these two vectors that come from the parameterization. So that's not a satisfactory thing to do. What's happening is that the tangent spaces to the sphere and the cylinder at that point are the same. They coincide. And therefore, in other words, it means that their intersection is actually a plane through 2, 0, 0. And of course, we're going from R3 to R2. What we hope for with a zero set is something that's one-dimensional, in other words, a curve. And a curve will have tangent spaces that are simply one-dimensional. But at 2, 0, 0, this example gives trouble. And of course, the problem is that the rank there is not maximal. It has rank 0. I beg your pardon. It has rank 1 at 2, 0, 0. There's a diagram on the next page. Here it is. This is a little bit gross and thick. This was done in Maple, and I wanted to have a high grid, a lot of sample points, in order to make the behavior clear, the behavior at this point here. This is 2, 0, 0. But it's a consequence of having all these large number of sample points that this is rather thick. Really, this point here should really just be the intersection of two thin lines passing through 2, 0, 0. You can see, I think, that when we're away from 2, 0, 0, we get a well-defined curve of intersection. I'm going up there, and a well-defined curve of intersection here, and also lower down and around at the back. So it looks vaguely like a looped figure 8 in 3 dimensions. And as a regular curve, it can be parameterized as a perfectly good regular curve, but it has this point of self-intersection, and as a submanifold of R3, that's a problem. Okay, it's well worthwhile working through the details of these two examples. Okay, that's all for now.